Alright, so welcome back everyone to our second C++ programming lecture. So what are we going to talk about today? So today we will continue on data types. I will present one very important data type to you that you need in order to solve various tasks. Then we will also talk about expressions, and expressions can be used together with statements and control flow in order to describe computations and therefore in order to implement your own algorithms that perform some meaningful computations. And we will also talk about the const and constexpr qualifiers. So those are variable qualifiers, which can be quite important. Alright, so more on data types. Built-in arrays. So what is an array and why do we need arrays? So as you already know, a variable can hold a value of a certain type. For instance, last lecture we had some integer variables which can hold some data, some values, some integer values. Here's an example. So you can have an integer variable by the name of I and you initialize that integer to the value of 42. The problem now is, what if you need 10 integers in order to solve a given task? That might happen to you, that you need several integers in order to solve a given task. And how do you get 10 integers? I mean, what you could do is you could enumerate some integer variables, so integer A, integer B, integer C, integer D, until you have 10 integers. But I mean, that's very tedious and not very practical, and it just takes time and effort. So here is that naive idea. You could do that, of course, but I mean, there exist better ways, like for instance built-in arrays. And what happens if you need like 1000 integers or even more? Then I mean, you cannot just enumerate 1000 integers, so it really doesn't scale anymore. So what you would use in such situations are arrays. So built-in static arrays can store n objects of the same type. That's very important. So you can declare a variable and say, here, this variable should be able to store 10 integers, for instance, or 1000 integers. And those arrays are static, meaning once you declared your integer variable, it cannot change its size anymore. So once you declared an integer, array, for instance, or an array of any other type, it's static in size, so it cannot change its size. And static also means that you have to specify the size of an array at compile time, in contrast to runtime. So later on, when we have a more detailed discussion on memory and memory management in C and C++, we will get to know what the difference really between static and dynamic memory is. For now, just keep in mind that built-in arrays are static. And those values in an array are stored in one contiguous block of memory. So one value is stored after the other. Let's have an example here. So you can, for instance, create an integer array of 4 integers in such a way. So you need a variable's name. Here in this case, we have a variable named array. You specify the type of that array. So in this case, we wish to have an integer array, so specify integer. And here in brackets, in squared brackets, you specify the size of that array. You specify its size. And then the problem is, now we have 4 integers, so to say, in one variable, but we only have one variable's name. So how do we access all those 4 integer values? And you do that by using an index. So you have that array's name, and then in squared brackets, you specify the index here. And it's really important, I already did the joke last lecture, so that computer scientists always start counting at 0. And this is because if you need to access an array, the first value is always located at position 0. So you always start with the index 0. So if you have an array of length 4, of size 4, so 4 integers, your indices go from 0 to n minus 1, so 3 in our case. And for instance, here in this example, we can just write some literals to those integer values contained in that array. So write a 10 at the array position 0, write a 20 to the array position 1, write a 30 to integer position 2, and 40 to position 3. And then we have all our 4 positions really. And you can also, of course, use those values in computations, or you can print them to the command line. So what is printed here? So here we access array at the index 0 and 3. So 10 and 40 would be printed to the command line. You can also read out a value of an array integer and assign it to another integer variable, for instance. For instance, here goes by the name of number. Be very careful, however, if you use built-in arrays, because they are not, I mean, they are safe if you use them correctly, but if you do not use them correctly, they will bite you. So never ever try something like this one here. So never ever try to access an array at a negative index, because the index of an array always has to be positive, or at least it has to be 0, but non-negative, so to say. So don't try this one, and don't go beyond the upper limit. So if you have an integer array of size 4, your indices, your valid indices are from 0 to 3 to n minus 1. 5 is not a valid index anymore. And if you just write random data to it, that's pretty bad. Because in such situations, you would have something which is called your indices are out of bounds. And once you do that, your program has undefined behavior, or the behavior of your program is undefined. That means anything could happen depending on your compiler's implementation. I already mentioned that last time, and we will hear the term undefined behavior quite a lot when dealing with C and C++. So what could happen? At best, your program crashes. That's a good thing here, really, because then you notice that your program contains a bug, and then you can fix it. That's not so good, that you have to put some additional effort in fixing your bugs. What even worse is if you have such undefined behavior and you do some rubbish computations, and then your program continues execution, because then the results of your program are nonsense, and you might not even be aware of that, depending on your domain, on your computation domain. So what is the underlying problem here? So I mean, usually you would never go and just use an index beyond the valid indices, of course. But the problem here really is that an array does not know its size. So once you specify an array variable, a static built-in array, so you give it some size, like 4. But then you as a programmer, you as a developer, need to remember that this array has 4 integer variables, or so contains 4 integer values, and that the valid indices are 0 to 3. But you cannot ask this array variable, hey, what's your size? In other programming languages, like in Java, for instance, if you declare an array, you can at any point in the program ask that array, hey, array, what's your size? And then you can make sure that you do not go beyond valid indices. But in C++, you don't have that. You have to remember that on your own. And yeah, this, of course, increases probability for out of bounds. What you usually wish to do is, if you program in C++, usually you would not use a built-in array anymore. What you would rather use is you would use a std array, which is an STL data type. It's not a built-in data type anymore, but it's just a wrapper data type implemented in the STL, in the standard template library. And this std array data type, it knows its size. If you have a variable of that type, you can ask the variable, hey, how many integers do you have? And then you can make sure that you do not go beyond the valid indices. Also, if you need a dynamic array that can change in size at runtime, then you would rather use std vector. So we will learn about those types later on in this lecture. So what else do we have? You can have, if you have an array, you can also have multi-dimensional arrays. So arrays can have multiple dimensions. What does it mean? You can specify more brackets, basically. And here's an example where we create a 2D array, a two-dimensional array, which is essentially a matrix. So again, we have a variable's name, we have its type, so we would like to have an integer array. And then we specify its dimensions, like here we wish to have a 2 times 2 matrix, a 2 times 2 array. And those are basically the rows and columns. And how do we access the integer values then? Yeah, we just use 2 indices per integer value stored in that array. Here we specify the array's name and we say, yeah, at the position 0, 0, I would like to store the integer value 1. At the position 0, 1, I would like to store value 2. You'll get the concept, I believe. And you can, of course, also read out those integer values again. So matrix at the position 1 and 0, you can store, which is essentially 3. You can store in another integer variable, for instance, and use it in some computations. Also, please observe that I forgot a semicolon here. So this code would not compile. Your compiler would throw an error at you and maybe even specify, hey, you forgot a semicolon, and then you would need to fix that. And this program code here on the left-hand side is pretty much analog to what you also could write in mathematics. So here we have a 2 times 2 matrix. All the values are drawn from the whole number domain Z. 2 times 2 shall be the dimensions, and then here you store some values. And you can also, of course, create arrays of arbitrary dimension, but in practice, what's the highest dimension that you can use in meaningful computation? So you need to use 2D, two-dimensional arrays quite a lot, and you also sometimes need 3-dimensional arrays, but that's pretty much it. I mean, you could use 10-dimensional arrays, but for serious computations, you usually never go higher than 3. Or what means go higher? You never really need dimensions higher than 2 or 3. Okay, all right. So let's now go over to expressions and how we can use and employ expressions in order to specify computations. That is what we eventually will do at the end of the lecture. So if you go to cppreference.com, you will find the following quotation. The following quote. So an expression is a sequence of operators and their operands that specify a computation. Expression evaluation, so apparently you can also evaluate expressions, and expression evaluation may produce a result, that's what we do today, and may generate side effects. So regarding side effects, we will talk about that later on, but for now, the first part is the important part. So operands can be variables or literals, and operands can be one of the following. Here, if you go to cppreference.com, you can find those lists of common operators, and you can see we have some assignment operators, we have some increment-decrement operators, which allow you to increment and decrement integer types. We have some some arithmetic operations here. We have some logical operations. We have comparison operations. Later on, we will need member access. I mean, already you observed member access because if you use those square brackets here to access values of arrays, that would be a member access already. But we will learn about those more exotic operators later on. For now, maybe let's have some examples of assignment operators and arithmetic operators, and maybe some logic and comparison operators. So let's have a few examples to get a better feeling how that all works. So let's start with an integer variable I, which we initialize to the value of 5. So what would the expression minus I evaluate to? So it's hopefully not too hard to see. So I's value is 5, and then minus I, the expression would evaluate to minus 5. Yeah, looks reasonable, I would say, and it's also implemented in the language like that. I plus 10, 50, sure. So I minus 5 times 2 times 2. Here we have to keep the operator's precedence in mind. So times and division before addition and multiplication. That means we would compute 5 times 2 times 2, which is 20, and then we are left with I minus 20. So 5 minus 20 is minus 15. 6 times 6, 36. That also looks reasonable. Minus minus I, so whatever the value of I is, decremented, and that would be 4. This is a more exotic operator, but you still needed quite a few occasions. And this is the remainder operator, or also the modulo operator. So that's basically give me the remainder of a division here. So let's perform a division. So 11 divided by 5 is basically 2, and the remainder is 1. So this expression here gives you 1 as a result. It's basically the remainder of a division. And you need that operator sometimes. It's quite useful. Comparisons. Let's talk about some comparisons here. So I equal to 5 is of course true, because I's value is 5. So that would evaluate to true. Please observe that 1 and true in C++ are equivalent. So it's the same thing really. What else do we have? I greater than 100. That's obviously false, or 0, because 0 and false are also the same thing in C and C++. I smaller or equal to 5, that would evaluate to true, or 1, because I is 5. 100 is greater or equal than 99, that's obviously also true. Okay, so maybe let's combine now comparisons and logic. And again, we consider an integer variable I by the value of 5. So this explanation mark here means negation. So we negate the expression on the right-hand side. So what we would do is we would check, is I equal to 5? Yes, it's true. And then we negate true and are left with false, because the opposite of true is false. Here we use a logical OR, so this pipe symbol means the logical OR. So that is, let's evaluate the left-hand side and the right-hand side, and then let's OR the results. And also, regarding operators precedence, the stuff that's in between parentheses is always evaluated first. So if you have some sub-expressions in parentheses, those sub-expressions are always evaluated first. So that's very important to keep in mind. So let's do that. I greater than 100, that's obviously false. Or I equal to 5, and this is true. And then if we OR the sub-expressions, we would obtain true. What else do we have? Maybe let's use another one. That is the logical AND. Also very, very important. AND and OR, very important. I smaller or equal to 5. Yes, that's true. And minus 10 smaller or equal to 1. That's also true. So the overall expression here, where we use the and, is also true. False or true, you could also have some Boolean literals and use the or, and this would evaluate to true. So what's very important is to keep the operator's precedence in mind. So there are some tables where you can look up what operators are evaluated first. Sometimes if you use some more exotic expressions where you have lots and lots of operators and operands, sometimes you need to look it up. But if you're lazy, and programmers usually are lazy persons, so you can also just use parentheses to order your expressions, because the stuff that goes into parentheses gets evaluated first. So if you are not sure, or if you are too lazy to look it up, use parentheses. For what follows, we need to revisit the assignment operator. So this one here is the assignment operator. So it's not the mathematical equality. So if you need a check for equality, as we did on the last few slides here, you would use equals equals. What the single equals is an assignment operator. So how can I use it? I mean, we already used it quite a few occasions here. But what does it actually mean? Here we have an example where we declare an integer variable by the name of value, and we assign the value 10 to that variable. So we initialize it really with the value of 10. And what does it mean in detail? What it means is basically, on the right-hand side of the assignment operator, we have an expression. In this case here we have a very simple expression, because the expression is just the integer literal 10. And what happens here now is we evaluate the expression on the right-hand side. In this case it evaluates to 10. And whatever the evaluation gives us as a result, we shove to the left-hand side in the variable of on the left-hand side. So let's have another example. So we have another variable by the name of other, and let's have a look on the right-hand side. So on the right-hand side now we evaluate the expression. So it's 2 times 2 plus 3. So this is 7. It evaluates the 7, and this 7 we store now in the variable other. That's the meaning. So, and such an assignment operator here has it's often called left-hand side for obvious reasons, and right-hand side also for obvious reasons. And on the left-hand side you have an L value, and on the right-hand side you have an R value for left and right. And on the left-hand side you have an L value, and an L value is essentially an address to some memory address of your computer. So basically it's a variable for now. Later on we can also have references and pointers on the left-hand side. We will learn about that later on. For now it's sufficient if we have variables, ordinary variables on the left-hand side. And an R value is an expression that can be evaluated to a value, and then this value is stored in the variable or in the L value on the left-hand side. That's the meaning. We can also qualify variables, and one important qualifier that I'm going to present right now, because this qualifier prevents you from making mistakes, this qualifier is the const qualifier. So variables can be qualified with const, making them constant variables. What's the purpose of that? I mean, first of all, my recommendation is, whenever possible, do qualify constant variables with the const keyword, because then your compiler can check if you really use those variables in a constant context, so to say. Let's imagine you are some engineer and you write some software which needs the value of pi. Then you could go on and create a variable called pi and make it a floating point variable of type double, and you declare it to be a constant double. That means that this value is used to initialize that variable, and after this initialization took place, you cannot change the value of that variable again. And this here is okay because this variable is initialized at compile time. And why is that useful to declare constant variables? Yeah, of course, the compiler then gives you an error if you try to change the value of pi, because, I mean, semantically it does not make sense to change the value of pi because pi is a fixed constant of mathematics. So it does not really make sense. You probably only really wish to read the value of pi and not modify it. What's also okay is if you have an expression on the right hand side here. So 21 and 21, that's a static expression. I mean, we have all the values that we need to evaluate the expression. And this expression here evaluates to 42. Is used to initialize this 42 variable, and it's declared as a constant integer type. So this is perfectly fine. It's initialized at compile time, and then you can use the value of the 42 variable, but you cannot change the variable in your program at runtime. This would also be okay. That would declare a constant double variable by the name of value, and it's initialized with the return value of a function. Next lecture we will learn more about functions. For now we just use them, so just believe me here at this point. And this is also okay because the variable value is initialized at runtime. This would give you an error because you cannot just declare a constant integer I and you don't give an initial value to I. Why is that? Because later on in your program, you would not be able to change the value of I. And the compiler just throws an error at you because that doesn't make sense. Having a variable without initial value doesn't make sense. And you would not be even allowed to change its value after here you introduce that variable in your program. Also, attempts writing to pi is now forbidden, so the compiler would give you an error if you try to assign a new value to pi because you just declared pi is a constant variable, so that would not work out. You could also not override 42. And what is okay, of course, is if you use the value of pi, if you read the value of pi. Here in this expression on the right hand side, you read the value of pi and multiply times 2, and whatever is the result of that computation, you store in a new variable a. And this here is perfectly fine because pi is only read. And you can, of course, also write it to the command line, print it to the output stream. So constant variables can be read, but never written to after initialization. And here be very careful, because in C++ never say never again. Because in fact, you can still override some of the constant variables, which you apparently you should not do, of course. So please don't. If you declare constant variables, please treat them as constants, and the compiler will warn you. But there are ways in the type system which allows you to go around that const declaration here. But my recommendation is, of course, use const as much as possible because it will prevent you from making mistakes. What else do we have? We have also something that's even stronger than const. It's called const expression, and it allows you to perform computations at compile time. So even before your program is running. At compile time is, I mean, in the world of C++, you have your program, your compiler compiles it into a binary, and then you can execute that binary. And using the const expression keyword, you can tell your compiler, hey compiler, please compute some stuff while you're compiling the code. And this is essentially performing computations ahead of time, which saves you runtime, of course, because your program runs faster once the compiler translated it, because some computations might have already been evaluated. So use const expression keyword for constant expressions. So variables, for instance, can be a constexpr, as qualified as constexpr variables. Here's an example. So you have a constexpr variable double variable by the name of d, and on the right hand side you have some expression. But here this expression, I mean all the values, all the operands of that expression are known. I mean just integer or real literals, real number literals, floating point literals. So that means the computation does not depend on any unknown stuff. So that computation could actually also be evaluated here, or this expression could also be evaluated at compile time. And if you make it a constexpr variable here, the compiler will try to evaluate that at compile time. And then in your final binary, you have that variable d, and it's already initialized with the final value that would be the result of that computation. So you compute it ahead of time in the compilation step, so to say. You could also have constexpr int, which you initialize to 12 times 12, and 12 times 12 would also be evaluated at compile time. You can also have functions declared as constexpr functions. We will talk about that next lecture, where we introduce functions. And the thing is, if you have constexpr functions, you can even do more powerful stuff at compile time. So that's quite neat, actually. But also, please note that constexpr, the constexpr qualifier produces constant values. So the variables d and I, for instance, cannot be changed anymore. So constexpr really also includes const. So d and I would be const once they are initialized here, and then you cannot change d's or i's value. So, and yeah, quick recap here. I already told you about C++'s workflow. So you have a compilation step, and you have an execution step. And in compile, you compile source code to an executable program. And if you can perform computation in this step here, you do not have to perform the computation in this step, where you actually run your binary program. And that means that your program will run faster. Okay, so constant expressions may be evaluated at compile time. So the compiler is, as it is oftentimes, free to ignore your constexpr qualified variables. But usually it will do it if the compiler can do it. Yeah, leads to increased performance, obviously, because it slows, but it slows down the compile time. If you do some heavy computations as constexpr, then it all happens at compilation, and then that means essentially that your compiler takes longer to produce the executable binary. Yeah, already told that. So now that we have expressions, let's go to statements, and let's discuss about statements and what statements there are and how they can be used. Because once we have statements, we can implement our first algorithms in C++. So what are statements? So statements are fragments of the C++ program that can be executed in sequence. The body of any function is a sequence of statements. So, and for now, we know our main function, right? And the main function has a function body, and in the function body, you have some statements. So we already know approximately how that looks like, but here we are going to explain it in all detail. So this we already observed earlier, but this is actually an assignment statement. This is a statement here. A statement has a right-hand side. This assignment statement has a right-hand side, which evaluates, in this case, to 16, and it initializes this variable on the left-hand side, I of type integer, with the value of 16. And also observe that after each statement, you have to put a semicolon. So each statement needs to end on a semicolon, so to say. You could also have such an assignment statement where you assign 10 to the variable j. You can also have such an assignment statement where you assign the value of the variable j, which is 10, where you assign that value to I. Basically, what that means is take the expression on the right hand side, so j is 10, so we have 10 on the right hand side, and we store that 10 on what is on the left hand side, in the variable or address or reference or pointer to the L value, so to say, on the left hand side. That means after our computer has executed this statement here, i's value would be 10, because we just we have overwritten it. Initially it was 16, but now after executing the statement here, it's 10. Exactly. So what we need for the exercises, for the next exercise sheet, we need mathematical formulas and some functions. We will learn all the details on functions in the next lecture, but for now we are just using functions, and you just have to believe me that this is the correct syntax. But then having that, it allows for more interesting exercise sheets. If you wish to use some mathematical functions, you can include the header cmath, which defines some interesting mathematical functions that you can use to encode some mathematical formulas. What this header file basically implements, for instance, or includes, are some functions like the power function. So you can raise one number to the power of another number. You can compute the square root of a value, of a variable. You can have the absolute value. You can compute a sine or cosine, and lots more. So if you wish to have a more detailed look at this header file, just go to this web page, and it will provide you a list with all the functions contained in cmath, and also it will tell you what all the functions do and how to use them. Exactly, we will talk about that in detail next time. So for now, we can just use them. So what is the C++ equivalent to x is the square root of 2, and x is a real number. So if you wish to write that in C++ code, it would look like the following here. So, I mean, you have a variable x, so also here we have a variable by the name of x. We have it as a double data type, so a double to approximate a mathematical real number. I already told you that floating point numbers in computer science are only approximations of mathematical real numbers. And here you compute the square root of 2, and whatever the square root of 2 is, we store in that variable. That's basically the meaning. You could also write something like this one here. So if I would ask you for what is the C++ equivalent to y is 1 over 4 times e to the 3, it would be something like here. You have a double variable y, and you have the following expression here basically. So 1 over 4 times, and then you call a function, and this is the exponential function here. And pardon me, here this would be a call to the square root function. And you give it as a parameter the value from which you will compute, from which you wish to compute the square root. And here that would mean e to the 3, to the power of 3. All right. So, what other statements are there in C++? What statements can you use? So, C++ includes the following types of statements. Expression statements, we already used them today. Already used them quite a few times. We will also have component statements, which we discuss on the next few slides. We have selection statements, which we will also discuss today. Iteration statements, also today. We also have some jump statements next time later on. We can have declaration statements that's basically, we just declare a variable, for instance. We could also later on declare a function, but here we declare a variable, but we do not give it an initial value. We don't give it an initial value, so we have a variable I, but it has no initial value. That's basically a declaration statement here. Then there are some more advanced try blocks or atomic and synchronized blocks, but we will learn about them later on. So one after the other. Let's talk about compound statements. So what are compound statements? Compound statements are often also called blocks, are braced enclosed sequences of statements. I mean, that sounds easy, and it really is easy, so there's nothing complex on compound statements. Essentially, that would mean, that would already introduce a compound statement, or this would introduce here a block of statements. So what you have is really, you have at least one statement, one or more statements. In this case, we have two statements here. And you would just have some parentheses around those statements, and then this would be a compound statement or a block. So not very interesting on its own, but later on we will learn why that might be useful. Here's some example that shows you what you can do with that, but you shouldn't really do that in practice if you can avoid it. Because what happens here? If you use scopes, then something like the following is possible. You can declare an integer variable I and assign the initial value of 1 to it. And then you open a new scope here. Here, this is a scope open, and here we close the scope. And I have indented the code in between to make it more readable. And so here we can print the variable I, and here it would print 1, because I's value is 1. But because here now we are in another scope, we could also introduce another variable I, which is different from the previous variable I, because here this variable I lives in a different scope. And if we have this cout statement where we print the value of I to the command line, here it would print 2. And yet we can introduce another scope, another nested scope, where we again have a variable I, same variable name, but this is in fact a completely different variable, but they only have the same name but in different scopes, so that's perfectly fine for the compiler. I mean, it's very difficult to read for us humans, but in this statement here, this print statement would print 3, because here the innermost I is used, and then we close the innermost scope, then we close the outer scope, and then we are basically in our original scope here, and then this cout would print the value of 1. In reality, please don't do that. So please do not have multiple scopes nested and always have the same variable, because it's really confusing. So please avoid it. So let's talk a bit more on scopes. So a variable, that was the previous example, can be defined in multiple scopes with the same name. That's usually not what you wish to do. And also one more note is that each name that appears in a C++ program is only valid in some portion of the source code, which is called scope. So here we have a scope where we have two variables I and j. We initialize I to 42 and we initialize j to whatever 42 plus 10 is, 52. And if a variable goes out of scope, so to say, it can no longer be accessed. Here's an example. So let's open a scope. Let's have a variable I and some initial value. And within this scope, where we introduce that variable, we can use the variable I to describe some computations. It's perfectly fine. But once we leave that scope in which the variable I was declared in, we can no longer access the variable I, because outside of the scope here, the variable I does not exist anymore. So here, if we write such code, the compiler would actually throw an error at you and would say, yeah, I mean, I does not exist in that scope or something like that. So I can no longer be used. All right, that was it on compound statements. Let's go on to selection statements here. And with selection statements, you can now construct some more interesting control flow. Because earlier I told you, yeah, your program usually consists of a bunch of statements, and those statements are executed in sequence, so one statement after the other. But that's not very powerful. That's not very interesting. So just a bunch of statements in sequence is not powerful enough. Because what you could not express until now, until the next few slides, is you pass if you achieve more than 50% in the exercises. And of course, here for this course, you also have to pass the final project. Otherwise, you fail. If you need to encode such semantics, you did not really have the possibility yet. We didn't have the tools yet, but we will get those tools in the next few slides, really, to express an analog idea in code. So we need conditional code execution, and for those selection statements, we have three kinds of selection statement. In C++, we have an if statement. So we have an if is a keyword, we have an if, then we have a condition, and then we have a statement. And the statement that we specify in the if statement is only executed if the condition evaluates to true. And the condition can again be an expression. We can also have an if-else statement. So else is also a keyword, so we can have a statement that is associated with the if part, and we can have a statement that is associated with the else part. And then we also have a condition. So, and the condition again can be an expression, and the expression then is eventually evaluated to true or false. And if the condition evaluates to true, then the if statement here, the first one, is executed. If the condition evaluates to false, then this statement here that is associated with the else part is executed. And we also have a third thing. We have a switch statement. So switches are kind of special. I will give you some examples on the next few slides. So switch also has some condition, some value associated with it, because switches are a bit more restrictive in terms of what can be a condition here. And then you have some statement associated with it. I will have some detailed examples on the next few slides. And now we need those compound statements, or blocks, as we call them on the last slides, because each statement here, which I wrote on here, statement, each of those statements can in turn, of course, also be a compound statement. So that cannot, a statement here can not only be a single statement, but also can be a bunch of statements that are executed if the condition evaluates to true. So let's have an example. By the way, yeah, I already told that an expression, that a condition is an expression that can be evaluated to true or false. Let's have an example on an if statement. So let's have an integer I, initialize it to 10, and now we can write the following code. If I is less than 100, then, and then here we use a scope. So this is basically a scope statement, a compound statement, sorry, that introduces a scope, and this is a compound statement or a block, where we have another statement which prints to the command line I is smaller than 100. And this if statement, so first of all, I is smaller than 100, so this would evaluate to true. So this compound statement, this block here, would be executed, which then prints that message to the command line. So, and if statements allow to execute specific code depending on the condition that you specify here in those parentheses. What else can you do? You can also only specify a single statement, and you can omit the braces here, the curly braces. So this would be the same semantic meaning that would lead to the same result. However, please, if you use if, else, and all those statements, please always do the braces. And yeah, many people like to omit the braces, but this is really a great opportunity to introduce errors, because maybe it's late in the afternoon and a colleague takes some of your code and modifies it, and maybe a colleague wishes to execute another statement in case this expression evaluates to true. Maybe he not only wishes to print something, but also he wishes to add another statement. And if you just write another statement behind this statement here, it's not executed conditionally, because this if here really is only responsible for the next statement that follows, which would be cout. And whatever statement you write after that is always executed, because the if is not responsible for it. And so to avoid that stupid mistakes, and I can tell you, people lost their jobs for introducing such mistakes, because depending on your domain and your application, that can be quite expensive if you introduce such mistakes here. So please always do the braces here, and always make it a compound statement, because it will avoid errors in the long term. We can also have if statements with an else branch. I already gave you that example. So here we have a similar piece of code, but we also now have an else part. So we have an if part and a compound statement, and we also have an else part and an associated compound statement. And if this expression evaluates to true, then this piece of code here is executed. And if this evaluates to this expression, evaluates to false, then this message is printed to the command line. Again, if you just wish to use execute an individual statement, you can leave the parentheses, and then you're only really executing the next very statement. But again, please don't do it. It's bad practice. And I mean, developers tend to think, oh, I'm very clever here. I don't do that mistake, but it will happen. Rather earlier than later, probably. You can also have some if statements with more than 2 branches. You could also write some code like the following. So you have an integer variable I and initialize it to 3, and then you check multiple conditions here. So if this expression evaluates to true, then execute this one. Else, if this expression evaluates to true, execute this one. Else, if this expression evaluates to true, execute this piece of code. Else, and this is the final thing here, so in all other cases, if none of those expressions here evaluates to true, but all those expressions evaluate to false, then do something else, then execute this statement here. Okay. Let's now talk about switch statements, or a switch statement. So you can also have switch. It's also a keyword. You can associate a condition to the switch statement, and then you have a statement. So how does it work? It's similar to the if statement, but it's optimized for whenever you need to check multiple conditions or many conditions. So it's really convenient if many conditions need to be checked, and switch is highly optimized for this purpose. So using a switch, I will tell you one restriction on the next slide if I recall correctly. It's a bit restricted, more restricted than having if else. But switch, if you use switch, the compiler is allowed to construct a certain thing in the binary, which is called a jump table. So the condition can be evaluated not faster, but you evaluate the condition and then you jump directly to the corresponding case and corresponding code that must be executed if the conditions are met. So how does it look like? It looks like the following. So you have a switch, you have an expression, and then you check, you have some cases. So basically you define some cases. So case, the expression is equal to this expression specified here, then the following code is executed. This is basically a branch, so to say. And after you are done specifying the code that shall be executed if the expression is your desired case, then you need to have a break here, add a break keyword. Break is also a keyword. And then you can specify some more cases. Finally, you can also have a default block. So if none of the cases in the above matches, then the default is executed, the default branch, and then you have break, and then you leave that switch. So let's have an example. I believe that's might be very convenient. So you could write something like the following. You could have a character C and have the symbol uppercase D assigned to it. And then now you can switch on the C variable, so on the value of C. You can here now define multiple cases. So case, the contents of C is in uppercase A, case, the contents of C is uppercase B, and or C or D. And then depending on what really is the contents of C, you would execute this statement, this statement, this statement, this statement. Or if none of the above cases matches, then you go to the default branch, so to say, and execute this piece of code here. And also observe that you should usually do a break after each case to exit the switch statement. Otherwise, if you would not have the break here, if you would have case A, then you would print that, and then you would later on jump directly to case B. But usually that's not what you want. There are some rare conditions where that might be desired, but we will discuss about that in the next exercise class, I guess. All right. So what number will be printed here? I mean, the number printed to the command line is, of course, 4, because C's value is D, and we check this case, and if we have that case, then we print 4 to the command line. So what would be printed if C is X, uppercase symbol X, character X? It would go to the default branch because none of the cases match, and it would print -1. And please observe that the C++ switch only works if the condition can be evaluated to an integer. So this only works for integers. I mean, there are some languages like Java, for instance, where you can also have a switch on strings or on more complex data types. But in C++, this only works for integers. And why is that? Because if you use such a switch construct and you have integers here, the compiler again can introduce an optimization. It can construct a jump table, which makes it very easy, very fast. It's just then one lookup to check this symbol here, whatever enters here the switch, and then you directly in one lookup execute. You can jump to the code that is associated with the correct case. So if you're interested in that kind of stuff, use Google to look up jump statements and switch in context of C and C++. All right, so we already did selection statements. Now, at last, I believe, we have to discuss iteration statements. Let's discuss iteration statement next. Also called and known as loops, of course. So why do we need loops in the first place? Maybe let's have an example. So the previous types of statements are still not quite powerful enough. Why is that? Because I mean, you can have some problems like the following easy problem here. compute a sum, calculate a sum from 1 to 100. You cannot really express that with our current knowledge in a convenient manner. Of course, what you could do is you could have an integer variable, and then on the right hand side you have the expression 1 plus 2 plus 3 plus 4 so on till you reach plus 100. If you are very smart, like the Gauss, small Gauss, the guy from mathematics, you can maybe immediately figure it out without doing the actual computations. But let's say we are naive programmers, so we actually have to compute the sum here really at this point. Then that's very inconvenient to write such an expression, such a large expression on the right hand side. And the problem gets even worse. What if we wish to compute a sum from 1 to 10 or 1 to a million? We do not really list a million integers on the right hand side or a million literals and add them all up. That's quite tedious, of course. And even worse, what happens if the number, the upper end, can be chosen by your user, by the user of your program maybe as a command line parameter? I mean, then you have a huge problem because you cannot write an infinite amount of programs up front, which then, depending on your user's input, gives you the right results. That's not feasible, that's not possible. So, what do we have in C++? In C++, we have 4 different kinds of loops. We have a while loop, we have a do-while loop, we have a for loop, and we have a range for loop, and we will discuss all those loops in detail on the next few slides. Yeah, I guess we just leave it there and go to the next few slides. So, let's use a simple for loop. And let's give ourselves the problem that we wish to solve. So, let's sum up the numbers from 1 to 100. So, I mean, as already mentioned here, this does not work out. It's very inconvenient. So better use a loop to compute that sum. What does the structure of a for loop look like? So a for loop has a list associated with it. I mean, for again is a keyword. It will appear in blue if you type it in your editor. And it has a list associated with it in parentheses. And in this list, you can specify an initial statement, which is purely optional. You can also, and here please observe that you need to do some semicolons in between. You can have as a second, so to say, parameter, whatever you wish to call that, a condition, which is also purely optional. And as a third parameter, so to say, you can have an expression. And then you specify a statement. And the statement, again, of course, can also be a compound statement. So, again, my recommendation, always do the braces, even if your compound statement only consists one statement. And here's an example. So, let's introduce a variable which we initialize to 0, which should hold our result, which we call then sum, because sum shall sum up all the numbers and its initial value is 0. Now we have a for loop. So, and the first part here of the for loop is an init statement, an initialization statement, where we introduce a variable by the name of I and we initialize it to the value of 1. And size underscore t is also a data type, and size underscore t is just another term for an unsigned integer, or an unsigned long, I believe. So this is just a type definition, so size t is just other term for unsigned long. We will learn later on about type definitions. So here we introduce a variable I, which is our loop counter. We will use it as a loop counter. The second part here is a condition. So if I is smaller or equal to 100, that's our condition. And then the third part is plus I. So whatever the value of I is, incremented. So add 1 to it, in other terms. And then to the sum, add the contents, the value of I. And this plus equal operator here is just shorthand for sum is v equal to sum plus I. Pardon. Which just means whatever the value of sum is, take the value of sum, add the value of I to it, and then the result please again store in the variable sum. So, and how does this loop works? So this loop here initializes the loop variable I. It then checks if the condition is true. So in the first round, so I is 1 at the beginning, then we check the condition here. 1 is smaller or equal than 100. Yeah, that's true. Then we enter the loop's body, so and execute the statement here. And after we executed the loop's body, we execute whatever is here as the third part, the expression which comprises the third part. So we increment the variable I. And now in the second round, I is actually 2. And we check again, is 2 smaller or equal than 100? If the condition evaluates to true, then we enter the loop's body and perform the computation here that's specified. And again, we increment the variable I, the loop counter here, the variable that we use as a loop counter. And again, we check the condition and so on and so on. And we loop around and loop around. And at some point, we increment our I, and our I at some point will be 101. And in this case, this condition here evaluates to false, and then we do not enter the loop again, but we just continue at our code execution here with whatever statements follow the loop. And please also note that variables from the outside of the loop can also be used inside, because here you see we defined a variable sum, and we can use that sum variable, of course, inside the loop's body. And we can also use the loop counter here in our computations, in our expressions. So once again, what's going on? So I is initialized, the loop counter, and it's done only once. Then the condition is checked. If the condition evaluates to true, we execute the loop's body, and then we execute the expression. So that's the third part here. Usually it increases the loop counter as in our example, and then we go back to step 2 and check again on the condition. And at some point the condition, hopefully, I mean it's in your hands, that the loop at some point also exits and the condition at some point evaluates to false. Then you skip the loop and continue execution on the code that follows the loop. So those are for loops. Let's have a different problem. Maybe let's sum all the numbers from 1 to 100, but this time let's sum the squares of those numbers. So, and the solution would be the following. Again, we need a variable that holds our result, which we call sum. We initialize it to 0. And then we have a loop from 1 to 100. Same game as on the last slide. And the computation is a bit different, but because here we just we not only add the loop counter to the sum, but before that we evaluate the expression I times I, which is basically I squared, of course. And then whatever I squared is, we add to the sum variable, and then at the very end we are left with our final result of the first 100 numbers cubed. Yeah, again, please observe that we can also use the loop counter variable inside that loop, and we can use the loop counter variable in computations, in ordinary computations. You can also, I mean, those loops can also have arbitrary step widths. I mean, here we have steps of 1. Also observe that we here, in this case, we use an I, which we declare to be an integer. It's also fine. The idea is why we use size t. So size, again, is a type def for an unsigned long. because most of the time it does not make sense to have a negative loop counter. And so if you declare it to be an unsigned integer type, that just prevents you from making mistakes. That's the idea behind that. But I mean, it can also be an ordinary integer, your loop counter. And you not only have you can also initialize that loop counter to 10. You do not always have to initialize to 1. You can initialize to arbitrary numbers. You can, of course, also have arbitrary conditions here. And the expression at the very end can also have some arbitrary step widths. So there's no need to increment. You can also add 10 to the loop counter I. But be careful. I mean, if you use loops, stupid is as stupid does. So what does this piece of program print? So maybe I give you a few seconds, or you just pause the video. Maybe that's a more convenient method here. So what does this print, that piece of code? It prints nothing, if I recall correct. Let's check. So we have a sum, initialize it to 0. Then we have some loop counter variable I, initialize to 1. The condition is I is smaller than 3, which is the case. So we enter the loop body, add I to the sum variable, and decrement I. Okay, it's perfectly fine. So I is now 0. And then we executed the loop body once, then we need to evaluate this here. So then we increment I again. So I is now 1 again, and we check the condition. And 1 is still smaller than 3, so same game. And you see, because we decrement I here and increment I here, so oh, pardon. So we have created an endless loop, and the program is now spinning in that loop forever. And we are never going to execute this print statement, so to say. So please be aware of that, because I mean, if you're new to programming, I mean, that can happen sometimes, that you accidentally create infinite loops. So we also have other kinds of loops. I mean, we talked about the for loop. We can also have another kind of for loop, which is called the range for loop, where you have a for range declaration and a for range init, and then you have a statement associated with that loop. I only explain that loop to you for completeness. We will learn about how and why that works later on. But for instance, you could declare a vector of integer. Vector is a type which we will learn all about in one of the next lectures. It's basically a dynamic array where we store some numbers in it, some integer numbers, and then we can iterate the vector here. And this for loop basically means for each integer in that vector. So vector is a container that can store integers here in this case, and we iterate each element of that vector. That's just more convenient. Where this for loop is used all over the place, this for loop is probably only used if you work with containers, STL containers, and vector is a container. So we will learn how and why that works later on. So let's talk about while loops. While loops are a different kind of loops, but at the very end, at the end of the day, all loops are basically equivalent. So, but how does a while loop work? So a while loop, we have the while keyword. Again, we have a condition that can be evaluated to true or false. And we have a statement associated with that while loop, which can, of course, be a compound statement. Do the braces. And if you wish to compute all the numbers from 1 to 100, if you wish to compute that sum again, we can do so, of course. We need a variable for the final result for the sum. Then we can create a kind of counter variable outside. So just have an integer I, which should be our loop counter, which we initialize to 1. And then we have this while loop here. And we check this condition here. And if the condition evaluates to true, then we enter the while loop's body here in between those curly braces. So, and then in this case we add 1 to the sum, and then we increment the integer I. And again, once we done one round, we again check if the condition is true. If the condition is true, we enter this loop again. At some point, if the condition evaluates to false, we skip the while loop and continue with our execution after the while loop. Again, please observe that you need some code that causes this while loop to be skipped at some point. Otherwise, you have an infinite loop, which you probably do not wish to have in your program, most of the times at least. So this is called a rejecting while loop. Why is that called a rejecting while loop? Because if the condition here is evaluated to false at the first time you hit the loop, basically, so if that is evaluated to false, you never ever enter this loop a single time. So that's rejecting a while loop, because you can completely reject it. Same as for loop, so stupid is as stupid does. You could also write such code here. So you have a condition that evaluates to true, then you enter your loop and it prints not wise to the command line. But then this condition can never evaluate to false, because the variable I is never modified within that loop. That means that you essentially have another endless loop, which is most of the time not what you desire. So usually one needs to leave a loop at some point. I guess you get the point. At some places, an infinite loop is exactly what you need. For instance, say you need to implement some special software for some microcontrollers or such things. Then you could also write such a for loop. So I told you that all components here in the list, in the parentheses enclosed list of for loop, are purely optional. So you can also have it completely blank, and then you can have a loop body associated with that for loop, and then this is infinitely many times executed. So this would be one way to write an infinite loop. Another way to write an infinite while loop is just while true, because true is a condition that always evaluates to true, because true is true. So also you created an infinite loop. What else do we have? I mean, this was a rejecting while loop, but we can also have a non-rejecting while loop. There also exists a do while loop. Here's an example. So again, you have some code, and you have those keyword combination do and while, and you have some curly braces here. And this loop is always entered. So once your computer executed those both statements here, then you enter that loop and immediately do whatever is in your loop body. And then after executing the loop body once, then you check the condition here. Then you check the condition. And if the condition evaluates to true, again you enter the loop body. If your condition evaluates to false, you skip over that loop. And this is called a non-rejecting while loop, because you execute the loop body at least once. That's the point. So we have 4 basic loops. So for loop, range for loop, which is used for containers. We have a while loop and a do while loop. And it's very important to keep in mind that all loops are equivalent. So each loop can be transformed in another loop. But you should use the loop that feels most natural for the current situation. So if you need to iterate all elements of a container, you probably wish to use a range for loop. If you need to do some, let's say, array indexing, it might make sense to have an ordinary for loop with a loop counter variable, and there might be some other situations where a while loop is more useful or suitable. when we talk about loops, we also need to talk about two other keywords that are very important here. So you can also break loops. So how to break loops, how to break the rules of those loops, so to say. You use the break keyword. It's quite convenient, I guess, using the break keyword for the task. And if you use break within a loop, the loop is left, basically. So your execution leaves the loop. So you could write such code here. I is 1, and I is, of course, greater than 0. So you would enter that loop, and then you increment I. And usually, if you just ignore break, then you check again your loop condition, and it would be still true because you increment I, so it never gets 0. It's always greater than 1. So, and usually you would have an endless loop here, an infinite loop. But once the computer sees your break here, your break keyword as a statement, then the loop is left, and you continue your execution with all the statements that follow that while loop. So it might be very useful if you combine it with some if statements. You can, of course, combine if and while and nest those kind of things. For instance, again, say you implement some software for microcontroller or such things, and you permanently wish to monitor some sensor values. So maybe you have an integer to store a sensor value, and you wish to monitor in an endless loop the sensor value all the time. So you get your sensor value by calling a function get sensor value, and you read it. And if your sensor value is 0, maybe that's some error condition or whatnot, whatever that means to your domain that you implement the software for, then you can leave and exit the endless loop with the break keyword, and then you can, I don't know, do some other stuff that is appropriated in this case. So breaking loops, but you can also just skip loop iterations. So breaking completely exits a loop, but there's also the possibility to just skip one loop iteration. So loop iterations can be skipped as well. And for that, you can use the continue keyword. So, and if you use continue in a loop body, it causes a jump to the end of the loop body, but it does not exit it, just the end. And then again, usually you start all over again, check the conditions, and may execute again. And yeah, it also might be very useful if you combine it with some if statements, depending on your task that you need to solve. Here's an example. So you have a for loop, which iterates from 0 to 9, so 10 iterations basically. Inside of that loop body, you have an if statement which checks the condition if I is not equal to 5. Then you use the continue keyword as kind of statement, and then that would jump directly to the end of that loop and would again start all over again here, but it would not exit the loop. So what will be printed? So what is printed here? We print the value I, because initially I is initialized to 0, 0 is smaller than 10, 0 is not equal to 5. So that means that we hit continue, and we start all over the place. And once the value I, the loop counter, is 5, then 5, of course, is not equal to 5. So we would not execute that continue, and then we would print 5. So eventually what will be printed is 5 will be printed to the command line. So here's a nice GIF that explains it. So that would be continue, because continue only jumps to the end of the loop, but it doesn't exit the loop. And so basically, if you would have used break, break would have landed on the other roof. That's the basic idea, and I hope using that GIF you do not forget. All right, so let's add another note on nesting. You can nest loops and if statements, of course. I already showed you a few examples, and this might be particularly interesting for the exercises, for the next exercise sheet. You can also nest for loops. For instance, in this example we have two for loops which both uses some loop counter variable I and j, and so we enter the first loop, then we enter the second loop, and we just perform whatever is in the loop, in the innermost loop's body 5 times. Yeah, the 0th time, first time, second time, third time, fourth time. So 0 to 4 is 5 basically, so we then print 5 hashtags to the command line. And then we are done with our innermost loop, and then we execute this statement here, which is essentially a new line. It prints a line break to the command line. And then again, we go back to our first loop and start all over again. And once we enter our outermost loop, we directly enter our second nested innermost loop, and again print that hashtag 5 times. Then we print a new line again and all over again. So 5 times, 5 times, so to say. And so what, pardon, what does this piece of code print? It prints such a nice rectangle to the command line. I mean, that's also a standard exercise in computer science. If you are at a beginner's programming course, and you will have to do such a thing, a similar thing in the exercise classes. All right, so what can you do? You can also, of course, nest not only loops, you can also nest if statements. So let's have an integer variable I, we initialize it to 15, and we can check a bunch of things now. So we can check if I is greater than or equal to 10. Yes, it is. So we enter this statement here, this compound statement that is associated with that if. Then we check this condition here. Is 15, if the remainder is the remainder of a division of 15 by 5, is it 0? Yes, it is, because 15 divided by 5 is is 3, and the remainder is 0. So we would enter this compound statement here that is associated with that second if, and we would execute this statement here basically, which prints this nice message to the command line. Otherwise, if the inner if fails, then we would execute this one here, and if the outermost condition here fails or evaluates to false, I should rather say, then this piece of code would be executed. Right, so you kind of see that you really can use those ifs and loops to describe some more meaningful and powerful computations now. What does this code print? I mean, we already gone through all the code. This statement here, I is greater than 9 or divisible by 5. So algorithm and program. Now we have all the tools to implement some programs. So how does it all work? How does an algorithm and a program relate to each other? So by now you already have a Turing complete language. What does it mean? A Turing complete language is one that can compute everything that a Turing machine can compute. And probably you know the famous computer scientist Alan Turing, who was a famous computer scientist before computer science existed in the Second World War. And he and some other guys cracked the Enigma code at Bletchley Park. You can, read books and view some movies about him. So quite interesting, quite clever guy, of course. And what does it mean, everything that a Turing machine can compute? Says that mathematical definition. That is, you can compute everything that is intuitively computable, whatever mathematics mean by that. That basically means you can compute everything that is computable. However, there are some problems in the real world that are so-called undecidable. And for so-called undecidable problems, you cannot find an algorithm that solves the problem for the general case in all cases, so to say. But everything that is decidable, that you can intuitively compute, that by now you can compute using the tools we just presented here. So if you're interested in Alan Turing, you can look him up on Wikipedia. You can also look up what a Turing machine is. If you're just bored of the coronavirus situation, you can also go to Netflix and watch The Imitation Game, a really nice movie, so quite entertaining. Can recommend it. So, algorithm versus program. So an algorithm is basically a description how to solve a problem. Yeah? You're faced with a problem and then you create an algorithm that solves the problem. So basically a recipe on how to solve a problem. What do I need to do in order to come up with a solution? And a program is basically an algorithm formulated for the computer, such that the computer can solve your problem. Because, I mean, once you have described an algorithm, a recipe, you do not wish to solve all the concrete problems in the world by hand, but rather you wish to formulate a computer program that applies your algorithm to solve all the problems that go in that category that you just wish to solve. And C++ programs are basically just algorithms described by using a bunch of statements, which we saw in today's lecture and had a look at today's lecture here. So, and now you have the first tools to formulate your first algorithms in C++. So, algorithms, mathematics, and C++. So, you can almost always translate mathematics to C++. And wherever possible, I will try to make links between mathematics and C++. So, how to obtain a solution for a given task. So how it usually works is that you start with a concrete problem that you wish to solve. Then what you do is you abstract the problem and you try to come up with an algorithm that solves the problem. You then go to mathematics and use all the tools from mathematics to formulate your algorithm, to specify the algorithm formally. So how does it work? How do I come up with a solution and describe it in a mathematical manner? And eventually, once you have your formalization in mathematics, you now start and implement your algorithm in a programming language, like for instance in C++. And the resulting program that implements the mathematical algorithm then solves the problem for some given inputs. That's the basic idea here. And again, I will try to make links between mathematics and C++ wherever possible. So in general, I mean, mathematics and computer science are very similar. I mean, there's a good quote from one of our professors or lecturers at Bielefeld University, which goes by like, yeah, computer science is mathematics with electricity. And yeah, there's some quite good truth in that. So it's really, really quite similar. So at last, what can we do now? We can now, for instance, calculate an integral of a function with the tools that we have. I mean, do you think that's a hard task? What I can tell you, with the tools that we have now, we can do it. We can compute an integral with just some for loops and if-elses, and I guess we don't even need if-else. So let's check. So let's give ourselves the task to solve that integral, so 4 over 1 plus x squared. And we wish to compute the value of that concrete integral from 0 to 1. So assumption, let's assume that we do not know how to calculate an antiderivative of f of our function that we wish to integrate. So we play the naive game. So what can we do? We can use a numerical integration approach, so a numerical integration approach, and it's just about 30 lines of C++ code. and it just uses simple arithmetic. And the great thing about modern computers are they are very fast at arithmetic, so we can compute integrals fast using numeric integration. And in case you forgot what an integral is, I mean, given a function, so this is a function 4/1 plus x squared. So we have here the graph of that function, and the integral of that function from 0 to 1 is basically the area under the curve here, under the graphs from 0 to 1 that we wish to compute. So, and the basic idea, I mean, it's very simple. The basic idea is that we evaluate this function here at many points between 0 and 1. So if we just plug in a value x here to that function, if we just plug in 0, we obtain pretty much 4, I believe, if my eyes are still good. And we can now just sample many points here between 0 and 1, compute the function's value at that point, and then add up all those sample points and divide by the number of samples that we just used to get a rough approximation of the area under that graph. So how do we do it? We need some functionalities from CMath, and we also need the output stream, the IO stream header file, because we wish to print the result to the command line at the very end. In order to avoid prefixing everything from the STL, we can just use using namespace std, such that we can avoid writing std : every single time that we use something from the STL. Then we have a main function, so our program's entry point, and we have the integral value, so a variable for the final value that we initialize to 0. Then we have another variable, and here observe that we use long double as a very precise approximation of a real number from mathematics. And this x shall be used as our sampling point, which we also initialize to 0. So x is our sampling point. Then we have another variable to specify the number of sample points we wish to use. I don't know how many that is. 1 million, I believe. So 6 zeros. And then we compute a step width. So I mean, we now wish to have 1 million sample points under this curve here, or in between 0 and 1. And now we can compute a step width. So how many width we wish to have between those sampling points when we wish to use 1 million points. So that's basically 0 minus 1, and then abs is a function that computes the absolute value. So if you give it a positive value, it stays as is. If you give the absolute function, which is defined in CMath here, if you give it a negative number, it will give you the positive version, so to say, so it gets rid of the sign. And this is basically from where to where. So from 0 to 1, so we just specify here 0 to 1 and then the absolute value. And we divide that range, basically, that 0 to 1 range, by the number of sampling points, 1 million. Ignore the static cast for now. Just believe me that it is better if we use it here. We will learn later why we have to use it. And then let's have a for loop that goes through all the sampling points. So it iterates from the loop counter variable n, starting at 0, till 1 million. And what do we wish to do now? So for each iteration, we wish to evaluate the function here that we finally wish to integrate, and we plug in the current value of x. So x is at the beginning, x is 0, so we evaluate that function at the point x, and whatever this value is, we store it in, or we add it up to our integral value. And then we increase the step width. So then we increment x such that we get the next sampling point, so to say. And again, we hit that loop, we enter that loop once more and do the next sampling point, and eventually we have reached all 1 million sampling points and have added up the function's value at those points in the variable called integral val. At the very end, finally, we have to divide by the number of samples that we evaluated. And this is then our final answer. So, by the way, this statement here is just shorthand for whatever the integral value is. Have the integral value's value divided by n, the number of sampling points, and store the result back into that integral value variable. And this is our final result. And we can now print the variable's contents to the command line and then just return 0 to the operating system, saying everything worked fine. And thus we have our final result. And this can be computed quite fast by a modern machine, and you get a quite good approximation of the value. And in the case you do not know what the value, the exact value of that integral here is, it would be pi. That it would be exactly the value of pi. And the more sampling points you use, of course, the better is your approximation of the pi value. So that would be pretty much it for today. So let's quickly recap what we talked about today. So I told you about built-in arrays and how you can use them. But I also told you, do not use built-in arrays, rather use std array or std vector, which we will learn more about later on. I told you about expressions, how you can specify expressions and how expressions evaluate. We talked about assignments, how assignments can be used to store the results of expressions in variables. We talked about qualifiers, const and constexpr. We discussed simple statements like if statements, while statements, so loops basically for statements and all that good stuff. We discussed about the cmath header file, which defines some quite useful functions from mathematics that you can just include the header file and that you can use out of the box. We talked about scopes and what's the use and idea of scopes. Statements, more advanced statements. More advanced statements are probably selection statements like if else, switch, loops, and here. And we also talked about how to nest such language constructs in order to perform some more meaningful, more powerful computations. And we also, at the very end, discussed on how algorithms and mathematics and computer science are related to each other, and how one can combine those things, those concepts. Thank you very much. That would be it for today. And then I would say see you in the afternoon in our live stream for the exercise class. And otherwise, see you in a few hours, I guess.